or oblique asymptote? Well, here's the general picture here. And well, in this case, horizontal asymptotes are described by in a similar way as vertical asymptotes. Dash vertical lines. Well, in this case, it's dash horizontal lines. And the way we describe those vertical asymptotes were by equations. X equals something, x equals a number, x equals 5, x equals 7. So equations that describe vertical lines. In this case, for horizontal asymptotes, we will describe them well as equations of horizontal lines, but in this case, they're dashed. So that's y equals a number. And well, horizontal asymptotes describe in a way the behavior of a function in the long run. I mean, in terms of applications, it's like in the long run. But in mathematical terms, it's more like the behavior of a function for large values of x. For example, if we have this function right here, and let me look at the third one because I think it's the easiest one to visualize. Well, so we have this tendency like this. And we're going to go towards really, really large values. In other words, we're going to approach x equals infinity. So what's the y value apparently being hit as we approach infinity? Well, that's going to be that y value corresponding to the asymptote, but not touching that asymptote and not touching that y value. However, as opposed to what we looked last time for vertical asymptotes, we described that that a graph cannot cross a vertical asymptote. That's actually a discontinuity in the function. However, that's not the same. That's not necessarily true for horizontal asymptotes because it turns out that it is possible that a graph crosses its own horizontal asymptote. And in fact, I think we looked at a graph describing that last time. So something like this, and we're going to analyze how to get those values where the function actually crosses its own horizontal line. Number one, well, let's look at the algebraic techniques to find horizontal asymptotes. So everything is described over here. So we have a rational function of this form, p of x over q of x, where again, these numerators and denominators have to be strictly polynomials, and those are described in this form. You know, that's a polynomial, that's another polynomial. So there's a couple of guidelines that we have over here. Number one, if the degree of the denominator, all right, let me use a different color. The degree of the denominator is less than the degree of the degree of the numerator is less than the denominator. That is, this n is less than m, which is this n and this m right here. So ultimately, what we do is look at the leading terms. You can, in a way, neglect all the lower degree terms that you see in these polynomials and focus only on the higher degree ones. All right? So that means whenever you see that the degree in the denominator is larger than that in the numerator, all you say is the horizontal asymptote is y equals to 0. Well, to illustrate this briefly, what if we have some rational function that looks like, well, y equals x plus 1 over x cubed minus x plus 1. For example, well, if we neglect all the lower degree terms, well, this function behaves like x over x cubed, which can reduce to 1 over x squared. Now, think about, in this case, well, horizontal asymptotes are about the apparent y value that gets hit as x gets really, really big. How big? Well, to infinity. So 1 over infinity, what do we get when we divide by infinity, or when we divide by a really big number? Maybe not infinity. Any ideas? Divide by a big number. What's the tendency here? There's one chair here if you want to sit there. Right here. Oh, right there. So any ideas what happens when we divide when we divide by a really big number? What's the end result?
Very small number.
Small, how small? So it gets smaller every time, right? To the point that it becomes what?
Going towards 0.
0, right? So that's why this is the asymptote y equals to 0, because basically it becomes nothing, right? So, well, the second part of the guidelines here, the degree of the numerator is either greater than or equal the degree in the denominator. Well, there's a few sub cases, if you will, in this case. Number one, there's case A where the degrees are the same. In the case where the degrees are the same, all we do is look at the leading coefficients in this case, a sub n and b sub n. And the ratio of those two numbers, that's the value of the horizontal asymptote. Really easy to do. And letter B, when the degree in the degree of the denominator, or rather the numerator, is one more than the degree in the denominator, then we're going to have a slant asymptote. And in this case, well, to get that slant asymptote, we need to perform the polynomial long division, and our result should be an equation of the form y equals ax plus b, which is, well, the equation of a straight line or a diagonal line, and well, that's going to be an asymptote. It's kind of weird to have like asymptotes that are in this form. They're so in the end, there's not just horizontal and vertical asymptotes, there's diagonal asymptotes. And in the last case, when the degree of the numerator is either 2 or more than the degree in the denominator, it's neither oblique nor horizontal. In fact, we would have to do the polynomial long division, and we will obtain a polynomial, and that polynomial will be our asymptote. And it's kind of weird to have like parabolic asymptotes, cubic asymptotes. Yes, it's that's a thing actually, um, but yeah, that's how it works. So let's have a look at some examples. Find the horizontal or oblique asymptotes if one exists. Well, so again, for horizontal asymptotes, we don't have to set anything equal to 0 and solve a polynomial equation. So all we do is, I think it's pretty straightforward. We just have to focus on the leading terms. So when we focus on the leading terms, we have x squared over x cubed, and we can see that the degree in the denominator, it's higher than the degree in the numerator. That is, we have the first case where m, actually this is, yes, where n is less than m. That means y equals 0 is the horizontal asymptote. We're not going to graph them for now. That's something we're going to do later. And yes, that's all we have to do for finding asymptotes. Notice they didn't ask to find the vertical, only the horizontal. We will do more of those anyway. Another example, find the horizontal or oblique asymptote if one exists. For the graph r of x equals 8x squared minus x plus 2 divided by 4x squared minus 1. Well, in this case, we can see by focusing only on the leading terms, the numerator and the denominator, just ignore everything else. Just focus on the leading terms. Notice that the degree in the numerator is exactly equal to the degree in the denominator. So what are we going to do then? Well, so just go with the ratio of the leading coefficients, a sub n over b sub m. In this case, a sub n is 8 and b sub m is 4, so that reduces to 2. So y equals to 2 is the horizontal asymptote for this rational function. Well, one more example, find the horizontal asymptote if one exists or oblique for the graph r of x equals to 3x to the 4th power minus x squared divided by x cubed minus x squared plus 1. Well, in this case, again, focus on the leading terms of every polynomial that you see in the numerator and denominator. And well, in this case, you can see that the degree in the numerator, that is n, is greater than m. But in this case, the difference in the degrees, they differ by 1. So that means we are going to have a slant asymptote. All right. Well, we need to find what that asymptote is, and we do this by polynomial long division, and that's something you might have learned. Of course, you learned back in high school, or college algebra. Well, I don't know what class you took before this class. So, let me give you some specifics about this kind of division because, well, whenever we set up a long division of a polynomial divided by another polynomial, we need to write the polynomials in descending order of powers. Well, in this case, that's what we have. However, there's a little issue here. And the little issue here is there's some missing terms. What do I mean by missing terms? There's a chair in the front. Yeah. Anyway. So the numerator, 3x to the 4th power. And, well, notice we don't have yes.
You're missing c in the top equation.
Missing c. Which one? Which c?
When you divide out, you'll have 3x to the power 4 minus x squared plus 0.
Oh, yes. So in this case, we're going to put some placeholder terms so we have everything organized by powers. Notice we don't have a cubic term. So what we do in this case, add a 0x cubed and then minus x squared. And then plus 0x and plus 0. So that way we have everything organized by exponents, by powers, and it's easier to add or subtract those terms when we perform the division. Well, so we divide by x cubed minus x squared. Notice we don't have an x to the 1st power in this case, so let's add it as a placeholder by adding a plus 0x and then just bring down the plus 1. And well, so to do the polynomial long division, no, this one, all we do is divide leading term of the dividend by the leading term of the divisor. And well, so we divide 3x to the 4th by x squared. That's going to be, that's 3x squared. However, we're going to put that 3x squared on top of the x squared term. Again, that's so we have everything organized by powers. I've seen many textbooks and many videos on YouTube just skipping this placeholder. I'm not a huge fan of it because sometimes you have like squares on top of cubics or vice versa, and then it becomes kind of a mess when it comes to adding and combining like terms. So that's why I encourage to have these placeholders. Well, so the next step to polynomial long division is multiply the result we get by the division and multiply by every single term in the divisor. That is 3x squared times, wait, this is supposed to be, where am I? Oh yeah. That's actually x only, right? My bad. So 3x times x cubed, that's 3x to the 4th. And well, something you might remember from polynomial long division is that we change the sign of whatever we get. For example, positive times positive, it's positive, but we need to change the sign. So I'm going to change it to negative so we can cancel out. 3x times negative x squared, that's 3x cubed. But well, in this case, positive times a negative is negative, but we need to change that to the opposite sign, which is positive, and then 3x times 0x, that's 0x squared, and 3x times 1, that's 3x. Positive times positive is positive, change that to a negative. So if you're wondering why do we change the sign, well, how about we go back to the basic division. So for example, the number with just numbers and no x's, 17 divided by 3, for example. So the question is, how many times does the 3 go into 17? Is that a 5? 5 times 3, isn't that a 15? But what's the process to finish the division here? Don't we subtract this? I mean, positive times a positive is positive, but well, we are changing the sign of whatever we get, right? So that's the same principle with algebraic expression. So that's why we change the sign of it. And well, we're ready to simplify this, cancel this. 3 plus 0 is 3, x cubed, and minus x squared, minus 3x plus 0. I mean, I know it's just a 0, but keep dropping it just for placeholding purposes. Well, the thing here, we continue working on the division as long as the degree of the first remainder matches the degree of the divisor. So in this case, it matches. And then in this case, well, 3x cubed over x cubed, that's a plus 3. And here is the thing. We would multiply every single term right here. However, that's not what we care. Ultimately, what we care is this result here, which is the quotient. That quotient will constitute the, not horizontal, the slant asymptote. We really don't care about just to save time, we don't care. We're not going to care about that part. So slant asymptote of the form y equals 3x plus 3. All right? So no need to finish the division. That's fine. Let's see. One more example. Find the horizontal or oblique asymptote if one exists for the graph r of x equals to 2x to the 5th power minus x cubed plus 2 over x cubed minus 1. Well, notice in this case, the degrees n is 2 more than m. So that is n, which is 5, and m, which is 3. So the difference between the degrees is 2. In this case, neither horizontal nor slant asymptote. In fact, if you look at the end behavior of this function, that is focused only on the leading terms, we would end up with 2x to the 5th over x cubed, which reduces to 2x squared. And in fact, it's going to look like a parabola, but in this case, it's a dashed parabola. So we're going to look at these kind of functions later when we focus on actually graphing this kind of rational function, which is actually the next topic, if I'm not mistaken. All right, so let's see. Let's move on. Oh, yeah, that's the end of this PDF file. Let me move on. That's this one right here. All right. So, oh yeah, the next topic before looking at the graphing, it's finding the values where a function f crosses its own horizontal asymptote. Well, so here is the thing. The way we describe, again, horizontal asymptotes are by the equations y equals d, where d is just any number, like y equals to 5. That means a horizontal line at a y value equals to 5, for example, or negative 3 or 4/3, any real number. And all we have to do is simply set the given rational function equal to the value of that horizontal asymptote and solve the equations. And well, there's a couple possibilities. Number one, if the equation has a solution, well, whatever that x value, that's the x value where the horizontal asymptote intersects the function. But otherwise, if we have a no solution, which is quite possible, then in this case, there's no intersection point between that rational function and the horizontal asymptote. So let's have a look at one example. All right. So let's see, given h equals to 8x squared plus 9x minus 5 divided by 2x squared plus 1, determine the point where the graph crosses its horizontal asymptote. Number one, what's the value of the horizontal asymptote in this case? Anyone? Yes? 4. Y equals to 4. How do we get that 4? So it's at the ratio of the leading coefficients, right? Because in this case, the degrees match. So all we do is simply y equals to 4. That means that we need to set 8x squared plus 9x minus 5 divided by 2x squared plus 1 and set it equal to 4 and solve the equation. So this is a rational equation. We need to clear the denominators by multiplying both sides by whatever we have in the denominator. Well, that is 8x squared plus 9x minus 5 equals to 4 times the quantity 2x squared plus 1. And well, we have parentheses on the right hand side. Let's distribute the coefficient. That is 8x squared plus 4, 8x squared plus 9x minus 5. And notice in this case we can cancel the square terms. That's going to leave us with 9x minus 5 equals to 4. And although the original problem look a little harder, well, in the end, that's just going to leave us with a very baby equation, a linear equation. Solve for x, add 5 to both sides, that's 9x equals to 9. Divide both sides by 9, that's x equals to 1. And x equals to 1 is the value where the function crosses its own horizontal asymptote. Number one, how about we draw first that horizontal asymptote so we can get a better visual. So the horizontal asymptote, which is y equals to 4. And we'll see how in the end, the end behavior here is to get closer to the asymptote from above, not from below actually. And we'll see this intersection point. Doesn't that correspond to x equals to 1? So I think the algebraic work we did is consistent with our picture here. So horizontal asymptote, y equals to 4. The point of intersection is x equals to 1. And typically what we do is plug in that value of x into our original equation to get the y value. But we already know the y value, which is the horizontal asymptote, don't we? So just use that information. All right? So there's cases in which, well, this particular case, there's a point of intersection, because we got a consistent equation. So for example, if you get something like 3 equals to 4, well, that's a contradiction. 3 is not equal to 4, well, that means no solution and no intersection between horizontal asymptote and the graph of the function f of x. All right? The next topic for this section, well, we're going to do more about this topic when we get to graph using a really big algorithm here, in which we are going to gather a lot of information to put it together and then sketch the graph of a rational function. So the first thing before going into those details, so let's graph our rational function, but using transformations. You might remember this library of functions where you're given the parent graph for, say, y equals x squared. Well, that's a parabola. Y equals x, that's a diagonal line. What else? The radical function. And well, from there, you will look at all the possible transformations, such as horizontal shifting, vertical shifting, stretching, and reflecting about the x-axis, the y-axis, all those transformations that you might be familiar with. In this case, well, actually there's a little typo here. I forgot to type a power 2 for the denominator. So please change, for those of you who have the file, make sure to make the changes. Yeah, otherwise it's not going to work. So number one, forget about the 2 and the plus 3 and let's identify the parent function. Well, without the plus 2 and without the 3, that looks like y equals 1 over x squared. Right? That's a graph of that's going to be the parent function, 1 over x squared. And well, that looks like the graph where from either side that goes to positive infinity, right? And well, let me use asymptote with a different color, not red. I would like to save red for the transform graph. So that there's a vertical asymptote at x equals 0. I think it's clear from the function. I mean, you plug in 0 in the denominator and square it, you still get the division by 0 and well. So to graphically depict that is by a vertical asymptote and a horizontal asymptote, y equals to 0. Now we can connect this idea with the guidelines we saw before about the degree in the denominator to be larger than the degree in the numerator. All right? And well, so what does that mean? Let's go back first to the shifting, to the transformation. So what would the plus 2 do in this case? Would that do a horizontal shift or a vertical shift? Horizontal shift. In which direction? Well, it's 2 units, right? But in which direction? To the left. Recall that all the shiftings that you see inside parentheses, inside radicals, or as powers of exponential functions, those mean in the opposite direction as the sign that you see. However, what about this plus 3? So that's 2 units left. And what about this 3? What transformation would be describing? 3 units in which direction? Up, right? All right. So all we have to do in this case, my advice here is shift the asymptotes. 3 units up and 2 units to the left, and then from there just draw the 2 tails of the graph. So that is 3 units up for the horizontal asymptote and 2 units to the left. Oops. 2 units to the left for the vertical asymptote. And from here, well, I'm going to change colors here. I'm going to use blue. And there you go. That's our shifted graph. All right. Same concept, same thing, but in this case we're just focusing on rational functions. Same transformation, same shiftings. All right. Let's see what's next. Okay, so we have an example. Oh, the next kind of the next type of. Actually, there's a little typo here. This title right here should be steps to graph rational So that's the step to graph rational functions, and well, here's a list of steps. So we consider a rational function that is a polynomial over a polynomial, and we'll make sure that there's no common factors. If there's common factors, make sure to factor the polynomials, divide them out. If they divide out, recall those are wholes again, as we saw in one example. But otherwise, those would be, everything else, would be asymptotes. So number one, so we need some pieces of information to graph rational functions, such as the intercepts. That is the y-intercept by setting y equal to 0 and get, if x equals to 0 and finding y. The x-intercept or intercepts, there might be more than one intercept in x-intercept rather, and that is by setting the function equal to 0 and solving the equation. Step number 3, identify any vertical asymptotes and draw them like dashed lines. Well, we already got some practice on that. We're going to do more practice here. And determine if horizontal or slant or neither asymptotes. Well, and again, as dashed lines. Another thing we need to know is to determine whether the function crosses the horizontal or the slant asymptote in the case. And test for symmetry. Again, checking for symmetry gives us an idea of how the graph is going to look like. It could be symmetric about the x-axis or the origin. Those are the symmetries that we are, no, the y-axis or the origin. And well, to get the symmetry, we use the following guidelines here. So we determine whether a function is symmetric about the y-axis if the function is even. That is, if we evaluate the function at negative x and we obtain the original function, well, then it's even. But otherwise, if we get the function in the opposite sign, it's an odd function, which is a function that is symmetric about the origin in this case. If you don't get any of those, well, it's possible that the function is neither symmetric about the y-axis nor the origin. And then plot at least one point on the intervals defined by the x-intercepts and the vertical asymptotes. That's some calculations that we will do. You'll see about it. And those are to give us an idea of whether the graph is approaching a horizontal asymptote from below or from above. And well, you'll see how is that going to work. So let's look at one basic example. Graph f of x equals x plus 3 over x minus 2. So number one, let's get the y-intercept. To get the y-intercept, evaluate the quantity f of 0. So that's 0 plus 3 over 0 minus 2. That is negative 3/2. And recall that intercepts are supposed to be expressed as order pairs. 0, comma, negative 3/2. For x-intercept, what do? Well, set the function x plus 3 over x minus 2. Set it equal to 0 and solve for the variable x. So number one, well, we have a rational equation. Let's multiply both sides by the denominator to clear the denominators and simplify the equation. And cancel this. And 0 times x minus 2, that's simply 0 on the right-hand side. Go over here. X plus 3 equals to 0 and x equals to negative 3. That means the intercept as an order pair corresponds to negative 3, comma, 0, because we said y equals to 0. The reason I'm pointing this out is because it's very common to make this kind of silly mistake to just mention the x value. Well, in this case, the x value only is just the 0 of the function, not the intercept. In this case, an intercept is a point, and a point, it's actually an order pair. And don't get me wrong, because some textbooks or some homework systems like well, one that comes to my mind, I think some of the Pearson, I'm not sure about the Alex one, but some other authors actually take just the x values as the intercept, but really the concept is that it's going to be the order pair. Well, let's identify vertical asymptotes, if any. Well, let's write down the function. And all right, question. How do we get vertical asymptotes? What part of the rational function do we focus on to get them? Any ideas? Yes.
The leading coefficients, right?
The leading coefficients, that's for horizontal asymptotes. Yes?
The bottom equation.
The bottom, so not just a coefficient, right? So what exactly about the bottom? Any ideas?
Set equal to 0.
Set the denominator equal to 0, right? Solve the equation. And x minus 2, set it equal to 0, and x equals to 2. It's a vertical asymptote in this case. So it's only one vertical asymptote. Now let's determine whether f has a horizontal or a slant asymptote. So now what about horizontal asymptote? So yeah, let's go back to the leading coefficients, and what do we get in this case? Let's put n and m together and determine whether n and m are equal or less than or greater than. Number one, they're equal. And what do we do when they're equal? Any ideas? Yes. We divide them. So what's the leading coefficient in the numerator? 1. And what about the one in the denominator? 1. I know it's kind of silly to write 1 over 1, but ultimately it's just to make sure that we know where they're coming from, right? So y equals 1 is then a horizontal asymptote. Let's see what else. Oh yeah, the next part, determine whether f crosses its own horizontal asymptote. That is, set the function x equals x plus 3 over x minus 2, set it equal to the value of the horizontal asymptote, that is, set it equal to 1, and solve the rational equation. Multiply both sides by x minus 2, that's x plus 3, equals to 1 times x plus 2, that's x minus 2. And notice the weirdness we're going to get. 3 equals to negative 2. And this is a contradiction. That means the equation has no solution. And therefore, f doesn't intersect its horizontal. I'm going to abbreviate HA for horizontal asymptote and VA for vertical asymptotes in the future. All right, so no, there's no intersection. What about symmetry? Do we have symmetry? Let's see. So let's evaluate f of negative x. Let me change plus 3 over minus 2 and change that x for, let me change it for a different color, change it to negative x, and negative x. Well, in this case, this is kind of weird because we neither got a, what's it called? Neither f of x in the end, nor negative f of x. So we didn't get the opposite in sign of the function, and we didn't get the function and it's not no symmetry in this case. Whoops. So no symmetry at all. That's more information. You'll see when we draw the graph of this. What else? Determine the behavior of f on each interval defined by the x-intercepts and the vertical asymptotes. So here's the thing. We're going to draw a line, and we are on the number line that we're going to plot. We're going to draw as a solid bubble all the x-intercepts, and as open bubbles all the vertical asymptotes. So as an x-intercept, what did we get for the x-intercept? We got negative 3. That's going to be a solid bubble. And we got a vertical asymptote that is x equals to 2. That's going to be an open bubble. Draw the number line. And in this case, we are going to choose test values to determine the y values, which will help us determine whether the graph will approach the horizontal asymptote from below or from above the horizontal asymptote. Well, and try to get the easiest numbers. I mean, as far as pretty much every number works, go easy with them. Negative 4, 0, and 3. This is what we're going to do. We're going to evaluate the original function at these three test values. That is f of -4, f of 0, f of 3. So let's do one calculation for f of -4. That is -4 plus 3 over -4 minus 2. That is -4 plus 3. That's -1 over -4 minus 2. That's -6. That's positive 1/6. All right. What would that mean? Well, we're going to get the following order pair. -4, comma 1/6. And well, I'm not going to show the calculations for the other two to save time, but you know how this works. Just plug in the values and you will get the y values. That's going to give us a -3/2 and 6. All right. So I think we have all the information that we need. That is 0, -3/2, and 3/6. Okay, let's put all the information together. That's more than enough information to sketch the graph of this function. Well, so I have a grid here to plot all the information. So number 1, let's get everything back. Okay, number 1. Well, you know what? I have the notes over here. I'm just going to use the information to avoid scrolling up and down. Well, so we have a y-intercept at 0, -3/2. That is, -3/2 is -1.5, so it's going to go somewhere here. So that's the y-intercept. The x-intercept is -3, 0. That's another piece of information here. The next piece of information that we got were the vertical asymptotes, and there's only one vertical asymptote, and that is at x equals to 2, right? We're going to use red for vertical asymptotes. Well, actually for all asymptotes. And what else did we get? Horizontal asymptotes, y equals to 1. The next step was to determine if f crosses its horizontal asymptote, but via algebra we found out that there's no such intersection. So what's next? Test for symmetry. Well, we don't have any symmetry, neither about the origin nor about the y-axis, and you will see when we sketch the graph. So now we're going to go to the test points that we got. These order pairs that we got over here, -4 or comma 1/6. That is -4 comma 1/6, which is, I'm going to estimate it like over here. And 0, -3/2, well, that's the y-intercept, that's fine. And 3, 6. So this means, okay, so the first test point that we got, it's to determine that the graph is approaching the horizontal asymptote from below. How do we know is that from below? Because, check this out. What's the y value? Oops. What's the y value for that test point? That's a 1/6. And what's the y value of the horizontal asymptote? That's y equals to 1. So clearly 1/6 is a number less than 1. So that means it's approaching from below the horizontal asymptote. And over here, 6, it's a number way higher than the horizontal asymptote, which is 1. So that means it's approaching from above. So all this being said, we have all the information. Oops. Forget to change. Whoops. I need to make sure I go through these 3 key points. I didn't go through. All right, that's one. And that's another one. And that's the graph of this function. And well, check the graph. Do you see any symmetry at all? It's not symmetric about the y-axis nor the origin. So, and we got that algebraically. All right. And here's the asymptotes, the key points, everything. All right. Let's see. Do we have time for more? Well, let's do it. Let's at least get some pieces of information about the second example. We're going to work on plenty of examples for rational functions because, believe it or not, pretty much every single case can be unique, and you will see as we progress through every other exercise. You know. So number one. Determine the y-intercept for this function that is evaluative of 0. That's 4 times 0 over 0 squared minus 4. Well, that's 0 over negative 4, which is 0. So the y-intercept is going to be the origin. And well, you know, the origin happens to be both x-intercept and y-intercept. But let's find out if there's additional x-intercept. So set the function for x over x squared minus 4, set it equal to 0, multiply both sides by x squared minus 4, cancel this, for x, 0 times this polynomial equals to 0, divide both sides by 4, that's x equals to 0, and like I mentioned before, this is again going to be the origin 0, 0, right? What's next? Vertical asymptotes. Oh, here's where we focus on the denominator of the rational function. And in this case, f of x equals 4x over x squared minus 4. Focus on the denominator, and x squared minus 4 equals to 0. There's a couple of ways to solve this baby quadratic equation, either by factoring the difference of squares or using not the zero product, it's the square root property. X squared equals to 4, and x equals plus or minus the square root of 4, which means x equals plus or minus 2. So there's two vertical asymptotes. That is x equals to negative 2 and x equals to 2. For the horizontal asymptote or slant asymptote, observe the degrees of the numerator and the denominator. Well, in this case, we can see that n is less than m. That is, the denominator in the degree in the denominator is higher. That means it's going to give us the easiest case. Y equals 0 is going to be our horizontal asymptote. Anything else? Determine whether f crosses its own horizontal asymptote for x squared minus 4. Set it equal to the value of the horizontal asymptote. That is the value of 0. But didn't we already solve the same equation when we got the x-intercept? We already got a solution for this equation, x equals to 0. All right, so that's the value of x where it crosses. But the order pair ultimately is going to be the origin. Again, it's not just solving the equation, it's not just getting the x value. We're looking for points because we want to sketch the graph using points, not just values. And